This video is section 8.5, solving exponential equations. An exponential equation is an equation that has the variable in the exponent. So this is an example of an exponential equation that we saw previously. With logarithms now, we have more tools to solve exponential equations. So we can do as we did before, which is solving exponential equations with equivalent bases. This is something that we saw in the previous lesson, whereby we try to make the base on the left side equal to the base on the right side, and then equate the exponents. So the first thing that I would do in this example right here, with this exponential equation, again it's exponential because we've got the exponent in the, the variable in the exponent. So what I'm going to do is I'm going to write 3 to the power of 2x minus 1 equals 108, and I'm going to take both sides and I'm going to divide both sides by 4. These 4's will cancel, and this will simplify to 3 to the power of 2x minus 1 is equal to, and 108 divided by 4 is equal to 27. Well, this works out really well, right? This is the first thing that you should try because 27 is a perfect power of 3. So 3 to the power of 2x minus 1 is just equal to 3 to the power of 3. So now that we have equivalent bases on both sides of the equation, we can equate the exponents. And so we will say, therefore, 2x minus 1 is equal to 3. Bring the 1 over to the other side. 2x is equal to 3 plus 1, or 2x is equal to 4. And then divide both sides by 2. Okay, to isolate the x. We end up with x is equal to 2. Okay, just reviewing, we simplified both sides, then recognizing that one of the sides could be rewritten as a power of 3. Now that they have equivalent bases, you equate the exponents and you solve. We can also solve exponential equations with logarithms. By taking the logarithm of both sides, you can take advantage of logarithm laws. This may or may not result in a number that will need to be approximated. So in this case right here, if we have 5 to the power of x is equal to 35, I know that 35 cannot be expressed as a perfect power of 5. So I can't change that into 5 to the power of something and then just equate the exponents as we did in the previous example. That won't work. So what we're going to do here is we are going to take the logarithm base 10 of both sides. Okay, so we're going to take the common logarithm of both sides. So therefore, common logarithm, so I'm not going to write the base, it's 10, 5 to the power of x is equal to common logarithm 35. Recognizing that I have a number, I'm taking the logarithm of a number raised to some exponent, I can use the power law. And the power law is something that we learned last lesson. So I'll bring up the logarithm laws so you can see them right now. Okay, so you can see the various logarithm laws in the that we learned in the last lesson. And we know that if we take the logarithm of a number raised to some exponent, that exponent can be brought forward in front of the logarithm as a coefficient. So effectively, what I can do right here is I can take this x, which was in the exponent, and now bring it in front as a coefficient. So the next line will read as follows. X, common logarithm of 5, is equal to the common logarithm of 35. Okay, this is much easier to solve now because this is just multiplication. And in order to isolate x, I'm going to take both sides and multiply by log 5. That will cancel this logarithm, and then I'll be left with x is equal to log 35 over log 5. And then we put that into our calculators because our calculators will do the common logarithm. And x is approximately equal to 2.2. So that's your final answer right there. Okay, so all we did is we took the logarithm of both sides of those equations, took advantage of the power law, and brought the x exponent down in front as a coefficient, and then isolated using our algebraic techniques. Okay, moving on. Okay, this is where things can get a bit tricky. Solving exponential equations using factoring. So these are more advanced ways of solving exponential equations. And they take advantage of both factoring and also exponent laws. So if we have 5 to the power of x plus 2, I have to remember that if I'm adding exponents, that means that what I probably had originally was 5 to the power of x times 5 to the power of 2, because my exponent laws say that if you have the same base and you are multiplying two numbers of the same base, then you can add their exponents. So this is just 5x plus 2, right? So, I mean, we can also do, if the x is throwing you for a loop here, you could say, all right, well, 2 to the power of 2 times 2 to the power of 3 is just 2 to the power of 5. We just add the exponents. And so we're doing the same thing here. Well, if this is x plus 2, I can go backwards and split this up into 5 to the power of x times 5 to the power of 2 minus 5 to the power of x is equal to 600. And then I see that 5 to the power of x is a common factor in both of these terms. So I'm going to factor out the 5 to the power of x. And I'll get 5 squared minus 1 right there. Okay, so this is a number I can evaluate. 5 squared to the power of 1 is simply 25 minus 1. 5 squared minus 1 is 25 minus 1 is equal to 600. And then 5 to the power of x times 24 is equal to 600. And I'm going to divide both sides by 24. Okay, in so doing, I get 5 to the power of x by itself. And I get 600 over 24. Well, 600 over 24 is actually equal to 25. And now I can use my previous technique of creating an equivalent base. 25 is a perfect power of 5, and therefore x is equal to 2. And that's my final answer. Okay, so to review this question, I started off by recognizing that 5 to the power of x plus 2 is the same thing as saying 5 to the power of x times 5 to the power of 2, because I'm taking advantage of my exponent laws. If you have the same base and you are multiplying the numbers together, you would add the exponents. Okay, and then noticing that 5 to the power of x was a factor of both terms, I factored out 5 to the power of x, and I got 5 squared minus 1, which I evaluated to be 24. Dividing both sides by 24 yielded 25 on the right side and 5x on the left, 5 to the power of x, and then created the common base and solved for x. Okay, in this next one over here, we're going to use substitution. So again, this is a very another kind of advanced technique on solving exponential equations. I'm going to say let A represent (3 to the power of x). So instead of writing, okay, so therefore I can say A is equal to 3 to the power of x. So what I could do right here is I can rewrite this equation, and I could say this is basically, again, using my exponent laws, this is the same thing as saying 3 to the power of x, then squared, right? Because you multiply exponents inside and outside the bracket, right? So 2x is the same thing as x times 2, minus 12, 3x, plus 27 is equal to 0. If I'm letting a equal to 3x, therefore a, which is 3x squared, minus 12a plus 27 is equal to 0. And now what I can do is I can use factoring here. And so I can factor this into two factors. So two numbers that multiply to give me positive 27 and negative 12, and add to give me negative 12. Well, that is a minus 9, a minus 3 equals to 0. And so using my zero product principle, which states that one of these two factors here has to be equal to 0. Therefore, a minus 9 is equal to 0. That means that a has to be equal to 9, and then instead of a, I'm going to back substitute 3 to the power of x is equal to 9, and x is therefore equal to 2. So that's one possibility, x is equal to 2. The other factor that could be equal to 0 is a minus 3. So a minus 3 could be equal to 0. A is equal to 3. 3 to the power of x, therefore, is equal to 3. And x is possibly also equal to 1. Right there. Great. So just to go back and review, we let a variable represent 3 to the power of x. We took advantage of the exponent laws and said that if you have an exponent inside and an exponent outside, you would multiply them together. So 3 to the power of 2x is the same thing as saying 3x to the power of 2. And then substituted a for that, factored, got my two factors, one of them having to be equal to 0. I then solved for a, back substituted 3x, and then found the various exponents on both factors. Right? Okay, looking at the next question right here. Again, we are definitely going to have to take advantage of our logarithm laws to solve this question. 3x to the power, I'm not sure why I said 3. 5 to the power of x plus 2 is equal to 6 to the power of x plus 1. So I'm going to substitute in my, I'm going to bring in, rather, my logarithm laws, and we can see which ones we could use here. So as we see here, I've got the variable in the exponent of both, and I need to get rid of that. I need to bring that variable down, because right now it's in the exponents, right? So I can take advantage of the power law and take the common logarithm of both sides. And if I took the common logarithm of both sides, let's do that and see what we get here. So we would get log base 10, which I don't write, 5x plus 2 is equal to log, common logarithm of 10, 6x plus 1. So I'm taking the log of a number with an exponent. And as you can see here, if I take the log of a number with an exponent, that exponent can be brought forward and placed in front as a coefficient. So this x plus 2 can then be brought forward here, and this x plus 1 can be brought forward here. So effectively, I've taken the x out of the exponent. So this then becomes bracket x plus 2 times common logarithm of 5 is equal to bracket x plus 1 times the common logarithm of 6. So this then just becomes an exercise in algebra, because I have to get x by itself somehow, but it's inside this bracket, and this log 5 is multiplying this bracket, which means that I've got to actually distribute this log 5 to both and do the same thing with this log 6. So I end up with a bit of a complicated mess here. I get x times log 5 plus 2 log 5 is equal to x log 6 plus log 6. Right? That's just expanding the log 6 into the brackets. I'm going to get all my x logarithms on to one side, so I'll put x log 5, and then I'll take this x log 6 and I'll bring it over, so minus x log 6. I'll take this 2 log 5 and I'll bring that to the other side, so then log 6 minus 2 log 5. I see that I have x common to both terms here, so I can factor out the x. Then I have log 5 minus log 6 is equal to log 6 minus 2 log 5. And I can see that by dividing both sides by the log 5 minus log 6 factor, log 5 minus log 6, that's a binomial factor because it's a binomial, there's two terms. That would cancel, and that would cancel, and I'd just be left with x. But I've got to rewrite it here, log 5 minus log 6. So I have an expression for x now. X is equal to log 6, common logarithm of 6, minus 2, common logarithm of 5, all over common logarithm of 5 minus common logarithm of 6. And then that's just a matter of inputting it into my calculator correctly, and I should get x is approximately equal to 7.8. All right, so starting from the top, we took the common logarithm of both sides, brought the exponent down in front, expanded into the bracket, and then just used algebra to isolate for x. Looking at the next example here, x is equal to log 38 base 3. Well, in order to solve for x here, we have to think of, okay, well, what could I use to find what the value of x is here, because I don't have I don't have the log 3 button on my calculator. Well, probably the easiest way to do this is just to use the change of base. Right? I could use the change of base formula. And the change of base formula states that log base 3, 38, or log 38 base 3 is simply equal to the common logarithm of 38 over the common logarithm of 3. And if this is equal to x, if log 38 base 3 is equal to x, therefore x is equal to the common logarithm of 38 over the common logarithm of 3. Inputting that into my calculator, and I get x is approximately equal to 3.3. Great. Homework is listed right here. As always, thanks for watching, and I hope you have a great day.